So that's a button. This one, that's a mouse. If you hold it down, show your mouse. Yeah, there you see. Yeah.
And you see it on the...
Yes, yeah. If you could ask the speakers to use that one.
Okay. Yeah, JWST boomer.
I don't need the full 10 minutes, so let's just. Another 3 minutes. More than a minute.
All right, everybody. I'm going to slowly get this party started as the people filter in. We're halfway, which is great with these talks. I'm excited. Before I forget, I should have mentioned, for those of you that want power, there's a power strip underneath your seats. Like, again, it's like an airplane. So when we're landing and taking off, please unplug your laptops though. Let's see. So this morning, as I was in the gym, I was thinking about the next steps. Remember, this is not a normal science conference where the output is you sharing your science results with other colleagues. It's also got the element of giving us input to figure out what to do next. And so I was thinking, how are we going to do this? And the talks that you presented and the comments in Slack are already fabulous, but I want more. So several minutes ago, I created a new Slack channel in the instance called Advise Us, very near the top, Advise A. And there's some instructions at the top, which I'll just go through in case you guys have any questions about it now. So you get 2 comments corresponding to 2 enhancements that you think would most help the community. It can affect the pipeline, it can affect data analysis tools, it can affect the calibration reference data, or something else, all right? It would be nice if you told us whether you think it's easy or hard. I'll be honest with you, if you thought it was easy and it turns out it's hard, that's going to mean that you underestimated the work and maybe would have chosen something else. But I'd just like to know whether you think it's easy, hard, or something in between. Extra credit, because I know you all want extra credit. Extra credit if you concisely explain why the enhancement is important. This is something we struggle with even internally. People say, we should put this new fabulous thing in, and I have to go back and say, exactly why? I mean, what do you imagine the thing is? It would help me. We'll figure it out if you don't put in why, but it would help. So 1 enhancement per Slack comment. You get 2 comments. You can start now. There are Slack comments. So as you see the talks coming today, you can change your mind and you can delete your comment or edit the one and just change what's in it or whatever. Then after the last break today, so in the afternoon, I will ask all of you to use the thumbs up capability in Slack to vote for the 5 enhancements that you think are most important. And of course, you can feel free to vote for your 1 or 2 if you have them, but I want to also have you guys go and vote for the other ones as well. And if you have to leave early, then you can vote early. That's fine. You wouldn't have your mind changed by the later talks anyway, because you wouldn't see them, right? So that's the plan. My decision-making cohort is excited about this plan. We do want to hear your input. So please do that. Any questions about that? Awesome. Do we have any other announcements? Remember, if you are speaking after the break and before lunch, we really need your talk in if it's not in already. They might all be in, I don't know, but I just have to say that. It's in my contract. Anything else? All right, well, let's get started with the first speaker then. I just sense a lot of energy in this room at 9 in the morning, I have to tell you guys. So there's nothing I can do to help you, but here we go.
No. You can flip the...
Sorry, I did have one more thing. I invite you, encourage you to Slack me individually with other thoughts you have about things we should be doing. I'm not going to ask you to post those publicly because A, you'd have to edit your things to be diplomatic to everybody who you might be talking about, and so. But I welcome it. So at any time this week, but today it would be awesome If you just have free-form comments you want to send me about any of this stuff, just Slack me, and everybody else will get it too. But just the simplest, if you just Slack the message to me to begin with. So thanks for that.
No, and it shows already online.
Ah, so you have to use that.
Otherwise, just go with your
Yeah, but it's
cursor.
not here.
It's not here.
I
Thomas.
don't know how to.
You work for any app or just PowerPoints?
I don't know how to. This one? Okay. Yeah, but we don't have the pump. Ah, okay. Okay. Good morning, everyone. I'm Michele Perna. I'm a postdoc at Central.
Sorry, could you just check if
Sorry. Can you hear me?
Yeah.
Okay, thank you. I'm Michele Perna, postdoc at the Center of Astrobiology in Madrid. First of all, I want to thank the organizers for inviting me and giving me the possibility to show the work I did in collaboration with many people within the NIRSpec IFU GTO team. Among them, I just want to mention Francesco De Eugenio, well, don't know. Okay. Francesco De Eugenio, Anna Ugler, Santiago Arribas, and Pablo Perez Gonzalez. Okay, so in the...
Yeah, there's a secret.
Okay. The first part of the presentation, I will introduce our survey, and then I will go through all the main artifacts we still see in the, at different levels in the products of stage 1, stage 2, and stage 3, and also our solutions for them. And in the final part, I will briefly talk about the PSF characterization and also the flux calibration. So for our survey, GANIS stands for Galaxy Assembly with NIRSpec IFS. The PIs are Roberto Maiolino and Santiago Arribas. The goal of this project is to characterize the internal structure and the closed environment of a sample of about 50 galaxies and AGN at redshift between 2 and 11. As you can see, most of them have been already observed in cycle 1. Yeah, so the idea is to use NIRSpec IFU to get the 3D layout of the galaxies, so essentially to combine the spectroscopic and imaging capabilities of NIRSpec. We have plenty of observations, observation configurations. So we have, for some targets, high-resolution data to trace the gas kinematics. For others, we have medium resolution and low resolution data to trace the stellar properties of these galaxies and AGN. So this is just a list of papers we published so far. I just wanted to highlight these two in which we describe our strategy for the data reduction.
Hey, online, make sure you're muted. Right?
This thing here kind of say correct.
Right? Okay. Can you please mute yourself?
Hey, Greg,
Greg?
for example, could you mute yourself, please?
Okay, yeah. I'll try
There
to
you
run.
go. Thank you.
Thank you. So for the pipeline overview, I'm not going to the details of the different stages. Here I just wanted to show you how the products, the stage 1 products and stage 2 products, so the count rate images and the 2D calibrated images look like for the NIRSpec IFU data. So for instance, for the count rate images we have here in the top and in the bottom, the 30 different slices of the IFU. In the middle, we have also the fixed streaks, but they disappear in the 2D calibrated images that essentially are showing the same information, but in physical units and after the corrections for instrumental effects. These are all the steps associated with the different stages of the pipeline. I'm just showing this image from the first J webinar, just to show you all the steps we are adding to this scheme. I'm using here 3 colors: green, orange, and red, just to highlight the amount of human and machine time required for each individual step. Essentially, I'm using the red, the green to identify the fast steps, the ones that are well implemented in the pipeline's workflow. In orange, the ones that requires a few hours of machine time and maybe also parameter fine-tuning. And in red, the ones that require a few hours of human time, and in particular require the visual inspection of the individual frames and also the use of some additional software. So I'm going to describe all these additional steps, but in the meantime, I just want to highlight that all the results I'm going to show you have been obtained with a modified version of this pipeline, 1.8.2. In particular, we patched the photon and the cube build as implemented in the 1.9.0. Okay, so let's start with the artifacts affecting the stage 1 results. I'm starting from the elongated cosmic ray streaks. They are shown here in this zoom in of a count rate image. Essentially, the pipeline was recognizing this streak here as a huge snowball, as you can see here from the data quality extension of the count rate image. The effect of this was the over subtraction of count rates in the region within this circle, as you can see from here in this image here. So our solution was a patch of the pipeline to fit ellipses to all the flagged regions consisting of a few pixels. And essentially, we removed all the regions from the list of these snowballs, all the regions for which the best fit ellipses have an axis ratio smaller than 0.1. This correction, was in some way implemented also in the pipeline 1.10. So this is not really relevant for us, but just to highlight that if you use a previous version of the pipeline, you may have this kind of problems. For the 1/f noise, we already talked a lot about the 1/f noise. The 1/f noise is essentially responsible of these stripes, vertical stripes. This is taken from the Bernard presentation. What we do is to model the 1/f in each column, so along the y-axis, with a low-order polynomial, after removing all the bright pixels with a sigma clipping. And here, again, is just to show you the original results we get from the pipeline and the ones we obtain with our solution. Of course, we can also use NSClean, the software developed by Bernard. And again, here, there is a comparison between the results we get from solution 1 and solution 2. If you want something more quantitative, I could say that at the end, we get almost identical signal to noise in the final cubes at spaxel level, but NScreen should be preferred in the, if we want to study the integrated spectra extracted from very large regions. In particular, here I'm showing the spectra extracted from a data cube reduced with NScreen in orange. The spectrum in blue, a spectrum extracted from our procedure, the one with single columns in blue, and for reference also in gray the expected trend of the background. As you can see in some regions here and also in the blue part, in the blue spectrum there are still some artifacts. This means that our procedure is not as good as NScreen. Okay, so for the stage 2 artifacts, I start with this zoom in of a 2D calibrated image. This is just to show you the presence of very bright emission lines in the different slices, here and also here. But in addition to the emission lines, we also have many artifacts. So for instance, saturated pixels, snowball residuals. At the edges of the slices, we also have uncalibrated pixels. And then we also have this leakage from failed open shutters. I want to point out that we have a small but increasing number of micro shutters that are stuck open and cannot be closed. Just to give an idea, these are all the MSA leakage regions I identified in an observation taken in August 2022, while this is what we have in June 2023. So as you can see, there are 2 new failed open shutters here. Okay. It is. MSA leakage is also affecting the flux calibration, in particular the S-flat step. This is the reference file used for the flat field correction. And as you can see, if we zoom in particular regions affected by the MSA leakage, we see some residuals from the MSA leakage subtraction. In other regions, it seems that the leakage was not subtracted at all. Here, for instance, but in particular also in this part here. Okay. And the S-flat is also introducing many bright outliers at the edges of the IFU slices. You can see here all these bright pixels. These are associated with unreliable S-flat in the data quality of the S-flat images, and at the end, they produce these very elongated structures here along the slices used to reconstruct the final data cube. So in order to solve all these problems, what we do is to generate DS9 masks to remove all the pixels associated with the MSA leakage to the residual cosmic rays, and also to the unreliable S-flats. Okay, let's move to the stage 3 artifacts, and in particular to the algorithms used to detect these outliers. I start with the old algorithm developed within the pipeline. It detects the outliers by comparing a median data cube obtained from all the ethers, resampled back to the detector plane, shown here. This is just one slice. So essentially, the previous algorithm was comparing this one with a single ether slice. The problem with this method is that there was a bug in WCS transformation, so at the end the comparison was not possible because of this offset of a few pixels. So what we did was to develop a different method, not relying on the WCS transformations. We simply used we adapted the Lacosmic procedure by Van Dokkum to the IFU. So essentially what we do is to calculate the derivative of the 2D calibrated images along the x-axis. Then we normalize these values using a local median, or 3 times the error, whichever is higher. And then we reject all the pixels above a given threshold in percentile. And all the details are in the Eugenio et al. Okay, so just to give you an idea of the results we get, here I'm showing the integrated spectrum extracted from this region here. This is a data cube obtained with our modified outlier detection, while this one is the one obtained using the new algorithm implemented in the new version of the pipeline 1.11. Essentially, the new approach, as far as I understand, is very similar to ours, but it performs the derivatives along the y-axis, while ours is doing it along the x-axis. So I would say that there is a significant improvement with respect to the previous versions of the outlier detection algorithms. Still related to the stage 3 artifacts, the wiggles. These wiggles are related to the fact that the NIRSpec IFS is not really sampling well the PSF of of point sources. So to explain these effects, I just start from a figure from Smith et al. This has been also mentioned and described in the David Lowe paper very recently. So I start with a very ideal and uniform and curved spectrum shown here at level of the detector plane. Of course, this is ideal if we project this spectrum to the detector using the detector pixel elements. The spectrum will look like this. Of course, here the dispersion axis and the spatial axis are not oriented as the column and rows of our detector. So what we need is to correct for this, is to rectify the spectrum. Once we do this, we obtain this spectrum here. And now, if we extract the spectrum from a single row, this is what we obtain here. So essentially, this is very similar to the wiggles we see in the real data, in the NIRSpec real data. And in order to decrease the amplitude of these wiggles, we essentially need to integrate over a few rows. This is very similar, as I said, to what we see in the real data. Here, I'm showing in orange, the integrated spectrum of a quasar at redshift 3. Here you can see some broad line and narrow line from the quasars. This spectrum is compared with a single spaxel spectrum in blue. As you can see, the single spaxel spectrum shows all these wiggles that are significantly affecting the continuum and also the shape of the emission lines, in particular here and here for the H beta and the oxygen 3. And the wiggles I'm showing here in the bottom are just obtained as the difference between these two curves. Another thing to take in mind is that the amplitude and the frequency of these wiggles seems to vary across the data cube, and the wiggles are present in hundreds of spaxels of our data cube. So, as I said before, the simplest solution here would be to integrate over large regions. We have also another possibility, is to degrade the resolution of our data, for instance, using the EMSM algorithm instead of the drizzle. And in this slide, what I'm showing is are the wiggles we obtain in the nuclear regions for extracted from a drizzle data cube in comparison with what we get from the EMSM data cube. As you can see, the amplitude of the wiggles is decreasing a lot, but they are still there. So in order to remove them, we need to fit them with a sinusoidal function, a small portion of the spectrum, and we need to repeat the fit as many times are necessary to recover the spectrum. At least this is what I'm doing to solve this issue. And as you can see here, the combination of all the truncated sinusoidal functions is reported in red. So once we have a model for these wiggles, of course, we can subtract them. And here I'm showing in light blue the original spectrum with all these wiggles, and in dark blue, the corrected spectrum. Okay, so an important thing is that the frequency of these wiggles seems to change smoothly as a function of the wavelength, as you can see here in the bottom. And we observe the same trend also in all the other spaxels in the data cube. So this means that we can use this information to model the wiggles consistently in a data cube, also in those spaxels with a relatively low signal to noise, and so obtain a wiggle subtracted data cube. This method has been tested in many NIRSpec IFU data of bright quasars at high redshift, but also in local ULIX. The algorithm is available for download. You can find it on GitHub. And of course, you are free to download and use it. In this last part, I just want to talk a little bit about the PSF characterization and also about the flux calibration for NIRSpec IFS data. I can start just saying that the 2D SED analysis requires locally registered PSF matched JWST data. Unfortunately, this cannot be done at this stage because we are still missing standard star observations. In particular, the available ones are affected by saturation in the blue part of the spectrum and also have limited number of jitters. What we did, however, was to use the available data to try to constrain the shape of the PSF. This is shown in this plot, reported in Evgeny et al. And what we discover is that it seems that the PSF is elongated along the instrument slices. Here you can just refer to the gray curve here for the full width at half maximum of the PSF along the slices, and in orange across the slices. And another result is that at short wavelengths, it seems that the PSF is significantly larger than the one of NIRCam. And also it doesn't show any dependence with the wavelength. The last thing I want to mention is about the spectrophotometry-based color calibration for prism data. We are doing this analysis using the observations of 8 galaxies within our program with prism data in combination with NIRCam photometry kindly provided by JWST, Primer, and SIRS collaborations. What I'm showing here is the offset between the IFU and the imaging magnitudes for the 8 galaxies. They are represented here with these black dots. The black curve here is representing the fit, the polynomial fit of this data. As you can see, it seems that we need color term corrections for this data in order to obtain reliable SED analysis results. I also want to mention that here we are showing relative differences. The absolute differences can be as high as 30 to 40% if we compare the NIRCam with the NIRSpec observations, and this is in some way similar to the results shown yesterday by Michaela. And this is my summary. We are using many data processing methods to improve the data quality. In particular, we are using our procedure to remove the 1/f noise and also the NS clean. We are generating masks to remove all the artifacts associated with the stage 2 products, so MSA leakage, snowball, and S-flat. We are modeling and subtracting the PSF wiggles using these algorithm I showed before, and we are also applying this spectrophotometric-based color calibration for the IFU data to derive stellar properties. Of course, there are still many open issues. Calibration data are still required, in particular to better characterize the point spread function and also the line spread function for the NIRSpec IFU data. We also need probably more reliable absolute flux and wavelength calibrations. And we also need to still need to understand the nature of some features sometimes are appearing in our data cubes. Here I'm just mentioning this feature at 1.08 micron, which we see in some of our observations. It has a uniform intensity across the whole field of view, and we really don't know why it is there. And this is all I wanted to present. Thank you very much.
Excellent, thank you. You'll have some questions to answer online, but we're gonna touch on a few of them right now. One is sort of an operational question. Is the MSA leakage in the same place every time, or do you need to flag different regions for each target?
More or less, it's always the same. So what we are doing is to generate a mask for detector 1 and another mask for the detector 2. And more or less, we are in some way using always the same, but we are adapting a little bit them, because there are some shutters that sometimes are associated with some signal in some observation, but not in others. So yeah, more or less, it's not so bad in the sense that we can use what we did in the past, but we have to adapt them.
Good. Okay. And then there were a few questions about the outlier detection. One was mine. It sounded like you said that version 1.11 was similar in quality to yours, but then the image, it looked like there were a bunch of outliers left. So, what was your experience?
Yeah, the presence of outliers up there are associated with this wavelength range. So
okay,
it's true they are there.
Yeah,
I would say that there are just a few.
so it's better,
with
but
respect to the previous version.
okay,
That's for sure.
but still not as good as what you have in yours, right?
Yeah, but still don't know if this is just because of the direction along which we are doing the
Right.
the
Okay.
reviews. I
Got it. No, that's fine. And then another question. There was an update to the outlier rejection in the pipeline a few months ago. Detection similar in concept to LA Cosmic. Do you have any idea how that performs? Have you had a chance to look at that at all?
I think.
So you think this is it?
They are referring to this.
Gotcha. Okay, good. Perfect. Thank you. And then there was a question also about LA Cosmic. Using LA Cosmic, I don't know how you're supposed to say that, but anyway, I'm not in the field. On the very undersampled NIRSpec PSF LSF produce any difficulties, the undersampling? I guess the underlying premise would be cosmic rays look like single pixels, and so would a...
Yeah, probably, yes, that's true. This is probably the reason why we also use the masks at the level of stage 2, because sometimes the outliers are quite extended. So with our procedure, our procedure is not as good to remove any kind of yeah.
Okay. Yeah, I'm not sure whether anybody was. I don't think it was a question. Yeah, that's fine. Okay, let me see if there's anything. Yes. So why don't we switch to the next speaker? We have a couple minutes left, though, so go ahead and ask a question.
Thank you, Michaele. I have a question regarding the wiggling. When you fix that, did you take into account, because it depends on the object you are observing, some cases you will have emission of molecular lines that can be fitted to these frequencies. So how can you, because if we use your method maybe for another object which is emitting something similar to the wiggling, how can we take this into account?
Yeah, so I can show you the images, but in my presentation there was the case of the ULIRs. In the ULIRs you have these very broad bands. What we do is essentially is to mask them. So if you mask them, you are less affected by presence of these broad lines. Sorry.
If you press and in presentation mode, there should be the cursor.
What does this one do?
It's a cursor pointer.
Oh, okay. Oopsie. Right. Hi, everyone. My name is Melissa Shabande. I'm a postdoc here at SCSCI, and I work on transient, supernovae, dust formation, and understanding how much supernovae contribute to the total dust budget in the universe. So we have a lot of data in the mid-infrared using MIRI MRS, and we were trying to improve our background subtraction for this data because I'm going to tell you in a little bit that we need to measure the amount of coal dust, which depends on the absolute flux in MRS, and we made some improvements. We're still working on it, but I'm going to show you what we've done so far. So Ori Fox here at SCSCI, and I've been working on this. A lot of people on MIRI team have helped us, such as David, Tyler, Jane, and Mike. So I'm part of the transient science group at SCSCI. We have 4 PIs, Ori Fox, Suvi Gazari, Armin, and Lou Strolger. We have a lot of students and postdocs that work with us. We work on different transients such as supernovae, GRBs, work on dust formation, and we also have Bob that contributes to our group. So today I'm going to tell you about the advancements that we've done for MIRI MRS point source reductions with complex backgrounds. So just a little bit of a intro. I'm sure you all know MIRI MRS goes from about 5 to 27 micron. We have 4 channels, and each channel has 3 bands. So we have total 12 bands, and most of our targets are point sources that are faint in either totally faint or faint in some channels because of the science, because of how much dust they have. So on top is showing you the 4 channels and each with 3 bands. And in the bottom, I'm showing you a picture of sort of 4 channels of one of our targets. And the reason we're trying to improve the background reduction is, for example, here, if you look at this star formation region that is in our cube, we want to take into account different variation in the background. And as you can see, we can see that our point source, this one is a supernova that was around 50 days post-maximum. You can see how it changes throughout these 4 channels, and it almost disappears in channel 4. Oops. Oops. Oh. Okay, cool. So the background changes a lot throughout the wavelength region and also even every day. And we have different backgrounds for each of these different objects that we have. So for example, you can see here that the observed spectrum looks like this red spectrum on the top, and then if we background correct it, it gets rid of most of the thermal background. So one of the big issues that we have with MIRI MRS is the huge thermal background that the telescope has in channel 4 and a little bit in channel 3. And you can also see that the background changes even depending on what day of the year the object was observed. Oops. I think this thing doesn't work, the pointer. Oh, I'm using it. Okay. Thank you. Yeah, I'm just going to use the computer. Okay, so what are the difficulties that we have? So the pipeline is mostly designed for objects that have a dedicated background observed, or they are either isolated and very bright, or they're extended source, like a galaxy. Our main targets are usually supernovae, transients that many of them are faint and they're point sources. They have, since most of these supernovae are located in the regions of a galaxy, they have really high background or they have a varying background. We have too much thermal background in channel 4, which we need to get rid of to do our science properly. Background is different for each of our objects. We have about 9 right now. The standard pipeline does not produce a subtracted cube that we can examine after the spectrum is extracted. And the PSF of point sources spreads over the entire field of view of channel 4 because of the dependence on the wavelength. The field of the PSF changes in each channel, and in channel 4 over here, it spreads almost throughout the entire field of view. So these are the difficulties that we're facing, and we are trying to sort of reduce the effect of these with our method. So why do we need a better background reduction for our science? Because we need absolute flux in longer wavelength. Since if we have a lot of cold dust in these transient supernovae, they get pretty bright in channel 4, and we need to measure the absolute flux in channel 4 to measure the dust mass and figure out how much dust these supernovae are hosting. And if we cannot get an absolute flux number in channel 4 that we can trust, then we cannot do our science and we cannot measure the dust mass. We also need the absolute flux in shorter wavelength in some of our targets because of the dust precursor molecules, such as silicon oxide, that is around 8 micron. We also need to remove background emission lines. Since a lot of these supernovae are located in the regions of a galaxy, they could have some galaxy emission lines, such as neon, and some of our supernovae could include, let's say, a neon line, but we need to get rid of the background so we can trust those emission lines. We also need to examine the subtracted cube, see how much improvement we see comparing the non-subtracted cube and the subtracted cube. And some of our targets are faint, and we also need to match the flux of the MIRI spectrum with NIRSpec and shorter wavelength, because for a lot of our targets, we observe them with ground-based and also NIRSpec, and we try to create a full spectral energy distribution so we can measure the temperature. So what are the advantages of our method? We will produce a cube and examine the entire cube after the reduction and figure out how much background is varying among these objects. It reduces the thermal background more than the annulus background reduction that the standard pipeline does. It produces a reduced cube that we can see after the reductions. It works for both point sources and extended sources. And then we can adjust the background selection, as I'm going to show you in a little bit. So here I'm showing you our background selection. So what we do is that we start with our raw data. We process it through standard pipelines, stage 1, stage 2, stage 3, and we get a non-subtracted cube. Then what we do is that we try to select, let's say, 40 different regions, as you can see on the right. 40 different regions, and each of these regions represent that area of the cube throughout different channels. And the reason we do this is to take into account how much the background is changing throughout the cube. So these are, let's say, for this supernova, it's over here, and then we have these different regions, which are the same for all channels. And then here on the top, what I'm showing you is one of these regions selected in the non-subtracted cube. So it's over here. You can see it's not, channel 1 doesn't include much of that. And in channel 4, so the blue region is on the non-subtracted cube before subtraction. And then what we do is that we extract a spectrum of each of these regions. So let's say we have 40 different blue regions, so we have 40 different spectra of these background points. And here I'm showing you this subtracted cube. So what we do is that after we have these 40 different spectra, we take a median of that, and we end up with a master background, or we call it master background. Then we feed it back into the stage 3 of the pipeline, and use that as our master background to get rid of the background of the entire cube. And in the bottom is the cube after the master background reduction is done. And I've selected the same region here in orange to show you how much of the background we have reduced. So the blue spectrum is before the reduction, and then after the reduction, you can see what it looks like. And it's almost a 0. So these 40 different spectra are represented here on the left. So before subtraction, we've plotted them flux versus wavelength. You can see how much it's varying, especially in channel 4. So the mean background is the one that we use, mean or median background is the one that we use as our master background to feed it back into the pipeline. And it's shown here in red. And after subtraction, we did the same thing, extracted spectra of the same regions to show how much the background has changed. You can see that there's still a variation in the background, especially in channel 4, but the median background showing in red is almost 0. And that's what we were trying to achieve. So this is another representation of before and after subtraction. So on the top, you can see these 4 channels that are before subtraction. So channel 1, here this is only showing you a slice or the image 1 wavelength unit of the cube in channel 1, and then channel 2, 3, and 4. And then after subtraction, channel 1 and 2 don't change much, but you can see how much of the thermal background we have reduced in channel 4. So this is a supernova that has a lot of cold dust, and that is why it's pretty bright still in channel 4. Many of our targets get fainter as we go longer wavelength because they still don't have much dust or emission in channel 4. So what are the different applications of the science? So that cube that I showed you earlier, this one, the spectrum of that cube looks like the one on the top. So what you see here is the blue spectrum is the pipeline with the annulus background reduction, the standard pipeline, and the black is our reduction. You can see that most of the spectrum looks the same. But in channel 4, we have a huge reduction in thermal background. And for this specific supernova, we have a lot of cold dust. That is why it's pretty bright in all channels, especially in channel 4. And what we need to do for the supernova is we need the exact absolute flux in channel 4 so we can model the dust mass and get a accurate dust mass. So that is why it's important that we can trust this area especially so we can have a better measurement. What I'm showing you here in the bottom is an example of how we do this dust modeling. So we make a model. This is sort of a preliminary. It's not a great fit, but it's just to show you how we do this science. So we have a red sort of model spectrum that is made of different components, such as silicate, carbon, neon, and pH lines. And so initially, when we were trying to model the spectrum, we couldn't model channel 4 at all, and that's when we realized what we're getting is not physical, and this absolute flux in channel 4 should be much lower. We use this kind of modeling. We get a dust mass, dust temperature, and then based on how many components we use, we can say how much of each of these components contribute to the total dust mass in the supernova. For example, this one has some pH lines, has a lot of silicate, carbon. It has a 21 micron feature that is common in some of these dusty targets. And now we can do a better dust mass measurement. However, we still are not sure about if we can trust this channel 4. We're still working on it. As you can see here, so what I'm showing you in the background is the residual background spectrum after the reduction. You can still see that there's some variation here that is sort of reflected in the gray region, which is the standard deviation of all these 40 background regions. So we're using this standard deviation as our error of the spectrum. Another use of this method or for our science is other type of supernovae, such as supernovae 1A, which are the thermonuclear explosion of white dwarfs. So for these supernovae, we don't really need the absolute flux in channel 4, but we care about the emission lines and the equivalent width and the full width half max of these lines. Here in the black, I'm showing you the R reduction, and the red is a physical model that you can see how good the model fits the spectrum. And in channel 4, what we did is that we multiplied channel 4 by a number to reduce it to a absolute flux that matches the model. But you can see that a lot of these features actually match the model pretty well, which we didn't think it would be this good. This is another use of this method, or why we need a better reduction. So here I'm showing you another supernova. This one, it doesn't have a lot of coal dust because it was newly exploded. So this was about 50 days after explosion. So what we care in this type of supernova is looking at dust precursors before dust forms. And some of these lines are located around 8 micron. We also see a lot of hydrogen in this type of supernova because they still have their outer layers intact. And in order to do that, we need to make sure that for example, silicon oxide molecules that we see are not from the galaxy, but are from the supernova. And then we can model these lines and get a sort of dust mass or an upper limit for the dust precursors before dust forms. So this is the same supernova, but I'm showing you the full spectral energy distribution, going from 0.4 micron all the way to 27. You can see here we have the ground base, and then here we have NIRSpec. the blue filter, NIRSpec red filter, and then we have the MIRI MRS spectrum. And for these points, the square gray points are the images that was taken from the galaxy by a different team, and we used those to extract the photometry for the supernova. That's from the FANGS team. And you can see that here we didn't change the flux at all, so all these ground-based NIRSpec and MIRI match pretty well. And the only thing is that in channel 4, from those images, we got an upper limit for the flux. And you can still see there is an increase in channel 4. And what we needed to have is a spectrum that matches sort of this point. And we're still working on this issue. Oops. Here I'm showing you a difference between two cubes. So on the left is a supernova that was 50 days after explosion, going from 5 micron to 27 micron. And on the right is a supernova that has cold dust. That is, early on it's not as bright, but then it gets brighter in channel 4. So we have all these different types of science, and we need a better reduction for these data. So my summary is that Pipeline does a good job with a dedicated background and isolated, pretty bright, extended sources such as supernova 1987A. I don't know if you've heard of that. It does a good job for that because it's 100 times, about 100 to 1,000 times brighter than our targets. It struggles with faint targets with variable and high backgrounds. There's still too much thermal background in channel 4. And we have this code that is public on GitHub. We don't need dedicated background. It works for both point and extended sources. It produces a reduced cube that we can see after the extraction. We can adjust the background selection areas, and there is less thermal background in channel 4, but we're still working on improving this. Thank you so much for listening.
So thank you. We don't have time for questions, so Marco can switch to the online one, but we will do a question while we're switching. So if you could let Marco step in there. There are a few online. You'll be interested in seeing them and responding to them. But one was maybe you could comment on how you choose the background regions, exclude the science sources in the mask when you're figuring out where to put your squares.
We try to have the square in almost all areas, but depending on the target, let's say if our target is fainter than I showed you a region that was bright in the cube, but it wasn't our target. So if our target is fainter than that, then we try to not include that kind of region, because then it creates an over subtraction in that specific channel. So depending on what we see in the cube and how bright the target is, we pretty much the entire cube. Thank you so much.
Emily, we saw your screen for a second. Maybe you can try again. Good.
Is that good?
In presentation mode, yes. Perfect. Thank you.
Okay. So, hi everybody. I'm Amélie Canin, and I'm a software engineer in Toulouse, in France. I'm working for the PDRs for All team, and I will present you Haute Couture, an optimized tool for stitching MIRI MRS cube. And this work has been done in collaboration with the data reduction team of the PDRs for All team. So first, I will start with a quick reminder on MIRI. So as you know, and as presented before, the MIRI MRS is a spectrograph with 4 different channels, and each channel composed with 3 subbands. Each channel has different field of view, so like here you can see, has different spectral resolution and spatial resolutions, all between 5 microns and 28 microns. So our goal here is to create a cube with all the information and not that summarize the 12 cubes. So for this, we have 2 different algorithms. In the first one, we create a stitch cube between 5 and 28 microns that keeps the initial spectral resolution of each channel. So we just put together all the 12 cubes on all the wavelengths. And the second algorithm is a sharpening stitching algorithm. So here we also create a stitch cube between 5 and 28 micron, but we want the best spatial resolutions possible. So the one of the channel 1 short. So we kind of increase the resolution of the bad channels. And for this, we use the data from the PDRS4 program. So the PDRS4 is an ERAS program which observed the Orion Nebula in September 2022 with NIRCam, MIRI, and NIRSpec. So here we have the field of view of the NIRCam image. So on the Orion Nebula and the Orion bar, and especially we work on the PDRS region. So here in dash you have the MIRI observations, and we focus on the next slide just on the third pointing. So this one where there is the proplit D203506. So we focus just on this to verify our algorithm and if it's work well. So here we have the MIRI observation on this pointing for the 4 different channels in the H2 line for channel 1, 2, and 3, and random wavelength for the channel 4. And these are aligned by coordinate using DS9, and we can clearly see that we have different spatial resolutions with the size of the pixels and different field of view. And on the left, as comparison, we have the NIRCam image in the also in H2 lines. And above, we have the spectrum of these regions for the different channels. So in blue, channel 1, in green, channel 2, in orange, channel 3, and in red, channel 4. And we can see overlap between the channel, for example, here, and also jumps between 2 different channels. So here we have a little jumps, here also. And this jumps and this depends on the observations and your strategy of observations. And the goal is to have a spectrum that is continuous on this wavelengths. So first, we use the basic stitch algorithms, and we start with field of view reprojections. So for this, this step is to have the same pixel in each cube to compare the same things. So for this, we do a reprojection on all the cube in the channel 1 short coordinate, and then we only use the field of view corresponding to the intersection of the 12 channels to have information on each pixels. And we did this using the function grid data. Next, we have spectral interpolations. It's also to have the same pixel, spectral pixel on the overlap to compare the same things. So for this, we create a common spectral grid between 5 and 28 microns with a fixed steps. And we choose the number of points in this grid to respect the Nyquist channel theorem on each channel. And when we have a new common grid for each channel, we can do an interpolation for each cube using the function interpolate. So here we have an example of the interpolation in channel 3 medium. So in orange, it's the initial point from the data, and in blue, it's interpolating point. So we can see we have a lot more points, and we have the same shape. So next, we have the spectral stitching. So for this, we have two spectra, S1 and S2, and we choose a reference. Here it's the spectrum S1. On the overlap, we calculate the mean for S1 and S2, and after we have two different methods. In the multiplicative one, we calculate the ratio between the two mean, and then we scale the S2 spectrum with this ratio to create a new spectrum that is continuous. And in the additive method, we calculate the difference between the two means and then scale the S2 spectrum by adding the difference. In each case, we have a new spectra continuous. That is a new reference for scale for stitch with other channel. So we did this for each pixels and each channels. So we stitch two channels together, and with this new reference, we stitch the next channel and go on until the 12 channels. So here we have an example on our data using the multiplicative method. So in black, it's the result of the algorithm, so the stitch spectrum. And we can see that is continuous on all the wavelength range. We use the channel 2 long as reference, so this one. It's why we can see difference between the color one and the black one. And for the other, we can see the gain between the data and the stitch. And here it's the example with the additive method. So in our case, there is not a lot of difference between the two methods because of our data and because we have very few ratio. It's near 1, so not a lot of difference. So this quick summary of these algorithms. So in input, it tells the MIRI MRS fits file from the pipeline corresponding to the level 3 and the 12th pipeline, not the stitch one in MAST with the 4 channels. You also need the reference channel and subband. So in the previous example, it was a channel 2 long, and the stitching method, so additive or multiplicative. And as output, we have one fits file with an updated header, the science data cube, so using the previous method and the stitch one, and an error data cube, so with the error propagation done during the process of our algorithm. So this code will be made available, and we have to discuss with the STSCI maybe for an integration in the pipeline. So now the question is how to choose between multiplicative and additive method. And it's as you wish. It totally depends on your data, your observations, and your science case. So in our case, the scientists have calculated the rotational diagram. And on this diagram, constate that the additive method has better results than the multiplicative one. So we choose to use the additive method and not the other, just because we constate it's better for us, but it totally depends on what you want to do. And after, we have the sharpening stitching algorithm. So the goal is to have a cube on all the data and with a special resolution of the channel 1 short, which has the best resolution. So for this, we create a union matrix with all the field of view and all the wavelengths. So block matrix with a lot of anti-value or 0. So like here with different, with a channel 1 short, channel 1 medium, etc. And on this matrix, we applied a non-negative matrix factorizations to obtain the W and H matrix. In the W matrix, we have the elementary spectra on all the wavelength range. And in the H matrix, we have the weight corresponding to the elementary spectra for each field of view. No, so we can reconstruct all the matrix for each field of view. But here we are only interested in the channel 1 short because it's better resolution. So we just keep the submatrix in H to reconstruct our observations. And with this result, we can reconstruct all the cubes and have a stitch cube on all the wavelengths with better resolutions. And I forgot to say, this work is still in progress, but we are optimistic that we will have a good result in 30 days. So thank you for your attention.
Excellent, thank you. We have time for questions. There's already a couple in the chat. When choosing between additive and multiplicative, do you have some overall guidelines? The question comes up because if we have to choose in the pipeline automatically, we need some rules, right?
Yeah. I think, in my opinion, the best is to do both and choose the better corresponding in the science case. There is no perfect answer. It really depends on what you want to do with your data.
Gotcha. Okay. Yeah. Just as a comment, I in my role often get asked to provide multiple choices to the observers, but to the community, but it's already pretty confusing figuring out what all those data files are, and so then you multiply by 2 because there's 2 different flavors, and it gets really confusing. So. But it's certainly possible to add things like this as something for a subset of the community to access when they reprocess the data. Another question, so the pipeline can also produce 5 to 28 micron cubes directly from 2D data. Yeah, I should have read this first. I'm not sure I can parse it. Do you have a feeling about how the results compare? Ah, I see. So the pipeline can produce stitched together wavelengths in a cube. So how have you looked at those results from the pipeline and compared them to yours?
I compare in the I think January or February, not with the last pipeline versions. But I think at this time you can only stitch each channel independently, so channel 1, 2, 3, etc. And I think there is just a stitch with no scale, and all the data are just put together. And at this time, we haven't found how that is done. But yeah, in February, when we use the stitch cube from the pipeline, we have still the jumps between the channels.
Gotcha. Okay. Does anybody want to comment, or shall we just move on? Yes, you may. Hold on. Wait. Hold on means hold on.
Thanks, Jeff. So it's about the first question about choosing in between multiplicative factor or an additive constant. I think it, for example, I have done those things not in terms of, not for JWST data, but for all the spectroscopic data. And for example, if you're looking at emission line spectroscopy and you have to measure emission line fluxes, then adding something to the continuum means you are going to subtract it later. So adding a constant is not going to be useful. So I totally agree with the recommendation that it depends on your science, and we cannot just choose blindly whether it should be multiplicative or additive or set in the pipeline a default option. Thanks.
All right, thank you. We're going to move on to the next speaker.
Okay, quick sound check. Can you hear me?
Yep.
Okay, great. I'm 2 minutes early. Should I wait or should I start?
Of silence? Yeah, we'll just watch you on the screen. No, I'm kidding. Go ahead.
Okay, sounds good. Yeah, so my name is Jean-Baptiste Ruffiot. I'm a research scientist at UC San Diego. So what I want to present today are the techniques or data reduction approach that we came up with to enable high contrast spectroscopy of exoplanets specifically. So that means high contrast in this context means looking at like very faint objects, so exoplanets of brown dwarf next to bright stars. So they're typically spatially resolved, but very close, like an arcsecond or so, and very faint. So we need to either model or subtract very accurately the host star in order to recover the faint companion signal. So, and this is applied to the NIRSpec IFU. So my talk is going to be very much oriented towards NIRSpec IFU and exoplanet. However, I think all the techniques that I'm going to talk about, the ideas that I'm going to talk about, should be applicable to MIRI MRS, for example, or really any other science case for which you have blended sources like crowded fields, or like binary stars, or anytime you have overlapping signal in your IFU data. I think maybe some of the things I'm going to talk about hopefully might be relevant to you. Okay, let me see. Yeah, so we're pretty excited about JWST spectroscopy capabilities with like NIRSpec IFU and MIRI MRS that allows us to get moderate resolution spectra with like a resolution of 2700 from like 1 to 20 microns, which covers the entire SCD of an exoplanetary atmosphere. So this is a plot from Brittany Miles' paper showing the result from the early release science program on VHS 1256b. And so that spectrum is really rich in a lot of molecules, features that are typically not accessible from the ground. For example, carbon dioxide or the silica clouds. Maybe if the atmosphere was cooler, we could see ammonia. So yeah, very rich data. And so what we want to do is get that kind of spectroscopy for all of the directly imaged exoplanets. Because the thing is, this spectrum, VHS 1256b, is actually not really high contrast. It's direct spectroscopy, but VHS 1256b is like 7 arcseconds away from a binary brown dwarf, and the flux ratio between the two is about 1 in 100. So for all practical purposes, this is like an isolated point source. But we're getting more data and more challenging data. For example, this is a two-planet system, where, so you have B and C. The flux ratio of B is equivalent to the flux ratio of VHS 1256b, but it's at 1.7 arcsecond. So you can start seeing the diffracted light, the speckles from the star that's a little bit to the right, that we'll have to worry about. But we can still see it in a single slice. The data I want to talk about today is this one, which is a program led by Marshall Perrin. And the goal of this program was to demonstrate the high contrast capability of the NIRSpec IFU and figure out what data analysis techniques we needed to use in order to do this. And you can see in this case, the companion is 10 to the minus 4, the brightness of the star at 1.6 arcseconds, and you cannot see it. It's buried in the speckle noise. It's about actually the same brightness as the speckles at its separation. Turns out, this is actually not that hard. This is a good demonstration case because the contrast is not that bad. What we want to do in the future is looking, for example, at Jupiter analogs, the planets that are less than a Jupiter mass at more than 1 million times fainter than the stars and at less than an arcsecond away. And I think based on the techniques that I'm going to present, we think this should be possible. So there were talks already presenting the IFU. So I just wanted to show a cube of movies going through the different wavelengths to remind everyone that integral for spectroscopy means getting both the spatial information and a spectrum at each spaxel. Yeah, so like you can see here, the PSF that scales, that get magnified at longer wavelengths, that's your lambda over D scaling. And so your companion signal is buried in there. So our goal is to try to subtract, or at least model that starlight to recover the companion signal. And here I'm going to jump ahead a little bit and just tell you that we can do that. But that required rethinking a little bit the data analysis for the IFU. So yeah, just a reminder, like on the left, you have the reminder that this is a companion lost in the speckle of the star. And on the right, you have the spectrum that we extracted after PSF subtraction and spectral extraction. PSF subtraction and spectral extraction. And this is a spectrum from 3 to 5 microns with a NIRSpec IFU with the high resolution mode, the resolution of 2700. And the spectral features that you see in there is not noise. They're actually the molecular features in the atmosphere of that faint companion. So you can see carbon monoxide, carbon dioxide, methane, and water everywhere. So I said that required sort of a different analysis technique because, so Michele actually presented this earlier, but I'm just going to talk about it again. It's the wiggles. Here I'm calling them oscillations. The fact that the IFUs on board JWST are spatially undersampled, and the result of that is that when you reconstruct a cube with the pipeline, you'll get these very large oscillations in your spectra. So if you look at the upper right plot, this is the plot from David Loft's paper. If you look at the spectrum of a single spaxel for single exposures, you'll get amplitude, like peak-to-valley amplitude that are up to 40–50% of your continuum. Even if you combine different dithers for a single spaxel, you still get systematics at a 20% level. And if you want to try to do PSF subtraction, you need to do that spaxel by spaxel. And if you try to recover a companion that's like 10 times, 100 times, or 1,000 times fainter than your continuum, well, you can't, that's not really going to be possible with like even a few percent systematics, let alone with like 40–50%. And because we're trying to do PSF subtraction, we cannot do aperture photometry. We cannot combine flux together because we would lose the resolution that we need. So yeah, this was the slide to also explain where these oscillations came from, but that was already done earlier, but I'm still going to remind it. So on the left, you have an example image, a detector image of the NIRSpec IFU. On the right, you have like a zoom in on a small region at the bottom of the detector where actually the companion signal should be. So I've highlighted the trace that the companion should follow in red, and you can see that that's curved. So what that means is that you split the flux periodically over two different rows, and that periodicity leads to the oscillations that I illustrated, that I showed earlier. So a mitigation strategy that we came up with was, So these oscillations, what I should say is that they are not an effect of the extraction. They are not a limitation of the data. So what that means is that one way we can mitigate them is to just skip the extraction altogether, maybe, and work in detector space. So forward modeling the data in the detector images directly. And I think there's a talk later by Anna de Graaf, who probably came up with similar ideas for the multi-object spectroscopy mode. So looking forward to that. But so we still allowed ourselves to interpolate the detector images to have constant wavelength in the vertical direction. So that's not the case in the original detector image. So here in the middle image, just interpolated so that each column has a constant wavelength. That's okay because we're not undersampled in the wavelength direction. And if I take a cut, I'm going to get what we call what's being called the point cloud. So it's basically each pixel in that column corresponds to one position in your field of view, and that's irregularly sampled. So we'll have to work with that irregularly sampled point cloud to do PSF subtraction, spectral extraction. But it turns out that's possible. We actually don't need regularly sampled data to do anything. So if we combined, so that was a single exposure. We often have several dithers. So if we combine all the dithers, we get a slightly better sampled point cloud. I'm not going to get into the details, but like maybe like a side note here, it turns out the NIRSpec IFU dithering pattern is not optimal. It doesn't uniformly sample your field of view. But it's all like spatially dependent and chromatic. Just something to keep in mind. I hope the dithering pattern can be improved in the future. Yeah, just a side note here. But anyway, this combined point cloud is going to be our data. And if I take like a small sector that includes the companion signal, I mean, here in this case, we know where the companion is. So I can just define that sector of the data. That's going to be a smaller point cloud. We also took a reference star associated to our science observations that own point cloud, so it's its own sampling of the spatial dimensions. So we'll need to interpolate that at the position of on the sampling of the data. So we'll have to fit for some centroid, some scaling factor, but that's okay. We subtract the best fit model, and you get the residuals that are shown on the right. And you can see the companion popping up. The yellow disk there is the companion that was originally buried in the speckle noise. So then the next step, now that we have subtracted the stellar PSF, well, we can do spectral extraction, and we can do that by just fitting a PSF model from WebPSF. That's what we're doing right now. And we also fit it to that point cloud, so we can extract the flux. And if we do that at every wavelength, well, we'll get a spectrum. So this is a spectrum I showed earlier, and here we've added like a best fit atmospheric model. It's still a pretty rough model in this case. There's a separate work that's being led by Keelan Hawk from Space Telescope, who's doing the atmospheric characterization in much more detailed. But it's just to show you that, yeah, we got a very good quality spectrum, despite the fact that this was a high contrast companion, and you have all these molecular features in there. So that's a great spectrum. We're very happy about it. It's still not photo noise limited though. We're still limited by the special undersampling, by the fact that by the interpolation errors resulting from like interpolating the reference star on the data sampling. So we try to also push that idea of forward modeling even further and just skip any kind of spectral extraction altogether. So we tend to think of the data reduction as like, we get some data, we subtract the stellar PSF, then we extract the spectrum of the companion, we get a 1D spectrum, then we take atmospheric models, we get a chi-square, we fit them to that 1D spectrum, we get a chi-square, we define a likelihood, and we do atmospheric characterization that way. Turns out you can fully forward model your detector images. You can take your atmospheric model, combine it with a web PSF, project that on your detector, and define your chi-square and your likelihood in the detector frame. And so that's what we did here. In this case, because it's high contrast, we also need to add a model for the starlight. I don't have time to get in like the gritty detail of how we define each component of the models. But yeah, the idea is that we have a model of the companion, a model of the starlight in detector frame, and we can fit that, we can fit for the companion signal at every position in the field of view. So at every position, we can get a flux for the companion and an uncertainty on that flux. So if we divide them, we get a signal to noise ratio. So that gets me a signal to noise ratio map for the companion that's shown in the center of this slide. And you can see how like the companion pops up with a signal to noise ratio like 250. That's what I was saying earlier, is that when you look at a single image, you can't see the companion. It's actually a pretty easy high contrast companion. And so we can derive detection limits, called contrast curves, sort of like 5 sigma detection limits as a function. So flux ratio as a function of the separation to the star. That's the right panel. Ignore all, I mean, it's a busy plot, but you can focus on the orange, so the bottom curve at the bottom, which is our estimated sensitivity for the NIRSpec IFU. So we think NIRSpec IFU is able to detect companions that are 1 million times fainter than the star at like 1 arc second. And that's photon noise limited. And I think this is a really important point. This analysis, it should be photon noise limited. So if you integrate longer, if you look at a brighter star, or if you look at a fainter, not fainter, if you look at a cooler atmosphere with larger spectral features in there, you'll get better, even better contrast. So you can go down to even close to 10 to the -7 in the best cases. And that means that we should be able to open that new part of the parameter space for exoplanets. So this is showing the exoplanets with spectroscopic data. So you have the RV transiting planets at short orbital periods on the left. You have the large, far away, directly imaged planets on the upper right. And JWST should be able to open like the middle part of like the solar system analogs, the middle part of this plot, which we are pretty excited about. So this is my conclusion slide. Yeah, so modeling the IFU data in detector images is possible. It can mitigate the spatial undersampling and get photon noise limited detection of companions. What I want to say though, and that's what I mentioned at the beginning, is this idea of fitting your data in the point cloud or in detector space directly is not specific to exoplanets or not specific to the NIRSpec IFU. It's applicable to MIRI MRS. Like any crowded field, any binary star, anything could benefit from this kind of approach, because if you when you have overlapping signal, you might not be able to use aperture photometry to decrease the systematics from the wiggles, from the oscillations due to the undersampling. So the code that we use to do all of that is on GitHub, but the problem is right now it's still not really documented, so I don't know how useful it is to anyone else. But we're working on that. I think the goal for the next year or so is going to be to write documentation, tutorials, and so on. Thank you, everyone.
Very impressive. Thank you. So there's one question at this point. How much improvement would there be with more uniform spacing of the point cloud?
I don't have a number on that. But the thing is, for example, I was mentioning that our PSF subtraction here, we still think we are interpolation limited. I mean, this is just a first attempt. Like there's probably 1,000 different things we can try to improve that PSF subtraction, like better interpolation schemes and other things. But right now we think interpolation limited, and that means like if you have better sampling, then you automatically reduce these interpolation errors. And yeah, so like there's no doubt to me that a better sampling of the spatial dimensions would lead to significantly better, I mean, to less systematics. I mean, I don't have a number. Maybe it's going to be chromatic. Yeah.
Yeah, good. Well, there's one more question, two more questions. There's one more question now. I think you used WebPSF to model the star, is that right? Or
so for the PSF subtraction, we use a reference star. For the spectral extraction, we use a WebPSF.
Perfect, thanks.
Yeah.
And then the contrast curve is grayed out within 0.3 arc seconds, but it's theoretically possible. What are the blockers to working in that domain?
Right. So I didn't talk about that. It's the fact that our starlight model, so the model we use to fit for the speckles is empirical. So we use the data itself to derive an empirical model of the starlight, and we use it to fit the speckles. That means that if your planet is too close to the star, and you don't manage that well, you might get the planet signal in your starlight model, and that would lead to like self-subtraction in your model, and so you don't want that. This was just the first reduction. I didn't worry about that, but you could like at each position mask the location of the companion, get your empirical starlight model around after masking. Then that way you avoid contamination of your starlight model. So you can get closer by just like thinking about this a little more and investing a little bit more time. But at some point, if your planet is just on top of your star, well, you might need to go. You might not be able to get an empirical model of your starlight. You might try to get a theoretical model of the star. You might get systematics limited. It's theoretically possible.
Yeah, it's good.
But to be explored in the future.
Perfect. All right, thanks again. Please answer those questions online for posterity. And thank you everybody who's putting comments and questions in Slack. That's super helpful. It's time for the break. I want to remind you that there are people out there looking for your input on the search interface and the Viz tools. And we'll see you back here at 10:40, right? Wait, when 11. 11. I've learned how to add 20. 11. Thank you, everybody.